This is the lecture for Chapter 5, OpenIntro. I'm going to get started here by sharing a desktop, and we're just going to get going. This is a lecture on analysis of variance. So let's get this thing happening here. All right, here we go. The analysis of variance, the big point behind it is this is how you can compare two means together. So you have two groups, or sorry, more than two means. So you have 3 or 4 or 5 groups of participants or groups of observations, groups of subjects, and you want to compare their means and find out if those means are statistically significantly different, which means doing an inferential hypothesis test and determining whether the means are expected to be different in the population or not. Of course, they're different in the sample. They're always different in the observations you can see. So to shift your mind into what you need to understand the analysis of variance, shockingly, it's about variance and variability, because it's right there in the name, right? So think about differences between any numbers as being variability. Any difference can be expressed as variability, even if there are only two numbers. So for instance, let's say we have two worms. One is 3 centimeters long, the other one is 9 centimeters long. We can find the mean between those two things. 3 plus 9 divided by 2 is 6. We can square the deviations from the mean. So the deviation of number 3 from 6, or the 3-inch worm from 6 inches mean, the deviation of the 9-inch worm from the 6-inch mean, and those are squared. So 9 is the variance of the two numbers 3 and 9. So the point here is you can make a variance out of just two numbers. And the variance is one way of expressing the difference between the two numbers. It's kind of a cumbersome way, but it becomes useful for analysis of variance, as we'll see. You can look at the standard deviation. I'm going to talk about standard deviations first because they're easier to understand. But the analysis of variance uses variance instead of standard deviation. And the analysis of variance is one of the big reasons why we like talking about variance when standard deviation is so much easier to kind of grasp intuitively. So let's think about what we've already learned how to do. We've learned how to look at the variability within a group of data. So let's say we have two groups of worms, and we've got some sort of study to find out whether the acidity of the soil that the worms are raised in affects their length, like the size of the worms. So the worms from high acidity soil are 7 centimeters, 9, 5, 8, 3, and 4 centimeters long. That's your sample from the high acidity soil, sample A. Sample B is from low acid soil. And you can tell that on average they're longer, 8, 9, 10, 11, 9, and 6. And you can look at the variability. So group A, if you punch that into Excel like I did, or R, or just work it out by hand, the mean of that first group is 6 centimeters. The standard deviation is 2.3 centimeters, and the variance is 5.6. Well, squared centimeters, though we don't usually talk about the units for variance. It's just kind of abstract. Group B has a mean it has a larger mean, so the worms are longer on average, which you can see just by looking at the numbers. 8.83 centimeters, the standard deviation is 1.72, a little smaller than the other one, and the variance 2.97. So the average variance of those two groups, I should put S instead of sigma, the average variance is about 2 centimeters, 2.04 centimeters. And so averaging those two variances together helps us maybe get a better idea of what the average variability, the average standard deviation, of getting the average variability among all the worms, not just in one group. So we like it when we have multiple groups and you can take the data from all of them and you can get an estimate of variability from lots of observations instead of just a few observations. So that average standard deviation. Now this isn't really the way we do things. You don't just take the mean of the standard deviations, which is what 2.04 is, but that's the idea. You do it a little bit more complicatedly, but ultimately it's the same concept. You're just averaging variability. So on average, this is how much worm lengths vary among themselves. And the worm lengths are just regular observations, nothing fancy. The reason to keep that in mind is because of a few slides in the future. Graphically, we can say group A might look like this. Now, of course, it wasn't beautifully normally distributed. And these are not sampling distributions or anything. This is just regular distribution, just regular variability, regular observations. This is group A and group B. You could see that they kind of overlap a little bit like that. And the mean for group A is 6 centimeters and group B is 8. And I'm going to draw even non-smooth distributions with these slick little curves quickly here, just because it's easier for me to do, and we sometimes do that, even though it's not a beautifully curved kind of distribution. Just that's your observations. The standard deviation of group A, I'm going to represent that with this line, and the width of the line is sort of roughly relative to the size of the standard deviation. So group A, 2.37 standard deviation, group B 1.72. When you average them together, you get an average standard deviation across both groups of 2.04 centimeters. So that's the average standard deviation of all the observations. That's the average variability of worm lengths. Now notice that the variability doesn't have much to do with where the mean is. In this case, group B has a higher mean, but actually lower variability. Variability is about spread around the mean. So those are two independent concepts. Number one, where the mean is. Number two, how much spread is around the mean. And this is basic that we had in chapter 1 or chapter 2, but it's important to try and keep this straight as we go through this. So now we're going to make the leap. We're going to talk about between groups variability. To make this leap, you have to switch your mind and start thinking of each group mean as if it was just a single observation. Mathematically, we're going to treat it briefly like a single observation. So we're going to look at the variability among the means. So let's say the data set is just 6 and 8.83. Those are the two group mean centimeter lengths for worms. Group A and Group B. Group A was the high acidity soil and Group B was low acidity, I think. So the standard deviation of those two numbers is 2. You can figure this out. You can calculate the standard deviation on just 2 numbers. That's cool. And the variance of that is 4.01. So now we have another measure of variability, the variability between means, represented here as a standard deviation. Variability could be standard deviation or variance. So the standard deviation between means is 2. Now remember that the average standard deviation among all the data points was pretty close to 2. It was 2.04. So we compare those two things together. Note that they're pretty similar in this case. They're really very similar. So once we have those two estimates, the estimate of the variability of all the individual points, which we call the within groups pooled or average within groups variability, and we have the variability estimate between the group means, treating each mean as a single data point, then we compare them. And we ask ourselves, how big is the variability between group means compared to the average variability between regular observations? Now, if the variance of the means is about the same, that's what those two squiggly tildes mean in my little shorthand here. If the variance of the variability of the means from each other is about the same as the variance of the regular observations from each other, if those are about the same, then each group mean might as well just be another data point. The variability between means is totally and completely expected. It might as well just be random variability. It looks like random variability because the variance of the regular observations, that's telling us what we should expect for just random sampling variability. That's what we expect for variability. So if the variability between the means is about the same as this, then the variability between the means is itself just random variability as far as we know. As far as we can tell, there's not any systematic difference between the groups because the means of the groups are themselves behaving as if they were just normal data points. They're no more different from each other than your average any 2 data points would be. And so we would probably conclude that soil acidity does not seem to matter in worm length, even though it looked like it did if we were to take this logic seriously that I just walked you through, and we shouldn't because it's pretty sloppy and conceptual, we would say soil acidity doesn't seem to matter. So make sure you understand the logic going on here. This is important logic so that you can really get what's going on with the analysis of variance. Now, we're not really into analysis of variance yet. We're just talking about the thinking behind it. So let's do this again, but let's make the group difference very clear. Let's make the group means very far apart. So group A, we have some lower worm lengths thrown in there, and group B, we have some higher worm lengths thrown in there, and that'll make the group means different. Group A mean is 3.5, but the standard deviation isn't much different. It's still around 2-ish. And group B, the standard deviation actually remained exactly the same after I tweaked the numbers, but the mean is much higher. So 3.5 and 9.2, these are much further apart from each other than 6 and 8.8. So there's a much bigger difference between these means. They're more spread out. So the average variability within the groups again, so averaging together 1.87, 1.72, the average standard deviation is 1.8 centimeters. And on average, this is how much worm lengths vary among themselves, of course. And graphically, this is represented like this. 1.87 is the variability for group A, 1.72 relatively similar for group B. We average those two things together, and so our best estimate of how much worm lengths vary among themselves in general in the world is 1.8 centimeters. Now we look at that between groups variability. Once again, we think of each group mean as if it were a single observation. We ask about the variability between those means. In this case, the means are farther apart, so there will be more variability. 3.5 and 9.17. The standard deviation of that turns out to be 4.01, and the variance, of course, is that squared, so it's 16.05. The 4.01 has some more decimal places, some more values in later decimal places, otherwise it wouldn't really be an 0.5. Anyway, small details. So you've got the within groups variability here, and you've got the average within groups variability, we've already seen. But now you have a new kind of variability again. The standard deviation between the means, it's much bigger. So those comparisons, the standard deviation between the means is more than twice as big as the standard deviation of any given point relative to its own mean. So the average variability among all the means is about 2 or less than 2, or about, sorry, not means, let me go back. The average variability among all the individual regular observations is about 2, but the variability between the means is much bigger. It's 4. So we have a much bigger difference there. So again, we ask ourselves, how big is the variability between those group means compared to the average variability we would expect between any regular observations? Well, in this case, the regular observations, they were about 2 in their standard deviation. Their standard deviation, their standard difference from each other was about 2 on average, whereas the variability of the means was twice as big. So we had a big difference, which I'm emphasizing with 2 greater than signs. So if the variance or the variability among the means is much bigger than the variability among the regular observations, then the groups are a lot different from each other. They're more different than anything that can be explained by our best estimate of how far regular observations should be from each other. Our best estimate here is that regular observations should be about 2 centimeters different from each other. However, the group means are twice that. They're 4 centimeters different. So regular observation can't explain that. So we would probably conclude soil acidity does seem to matter. So if you don't get that logic, and it's perfectly understandable because this is the first time you've ever seen it and it's a bit of a brain twist there, go back and watch that section, the beginning of the video up until now, multiple times. It's about 10, 12 minutes long. But moving on, when you do an independent groups t-test, this is effectively what you're doing. You're measuring the within group variance in one group and the within group variance in another group, and you pool them together. Even if you're not using the fancy pooled error term that the book is so terrified of, you still pool together the variance, no matter which formula you use, to get some estimate of the average variability between 2 observations. That's the point of that pool, that variance. We're trying to say, on average, how different are those 2 things? Or sorry, on average, how much do the individual points vary from each other? And then the between groups variance is just represented by the difference between the 2 means. We don't actually calculate a variance for that when we do a t-test. We calculate a difference between means, and then we compare it, and then we standardize that difference by dividing it by the pooled variance, the pooled standard deviation. So, or the pooled standard error, actually, the expected variance in the population. So this is a different way. The analysis of variance is just a different way of arriving at the same conclusion as a t-test when you have 2 groups. If you were to punch into a computer with the same 2 group data, an analysis of variance and a t-test, all the junky stuff in the middle would look different, but when you got out the other side, you would have the same p-value, and you would make exactly the same decision about rejecting or not rejecting the null hypothesis. So they would give you equivalent answers when you're done. They would give you the same p-value. They're just different ways of getting there. You can get there by standardizing the difference between the means, by dividing it by the pooled standard error, or you can get there by comparing the variance between the means to the variance within the 2 groups, the average variance within the 2 groups. Same concept. Now here's the t-test when you have the groups way, way separated. You have small within group variance that gets pooled together, and on average it's still small. The average of small with small is small, but very big between groups variance. And so of course you're going to reject the null hypothesis here. But if you have highly overlapping, a lot of variability within each group, big variability within each group, but not very much variability between the means, then the between groups variance is not big compared to the within groups variance, and you don't reject the null hypothesis. In other words, the difference between the means is not big. So the big leap here is, instead of thinking of differences between group means, we think of variability among group means. It's equivalent. It's just a different way of looking at the same thing, but it allows us to leap into more than two groups, because you can have variability among 2 means or 3 means or 4 means or 12 means. Now, honestly, you don't usually go beyond about 5 or 6 because it's pretty hard to interpret what's happening then. But often with about a handful of means, we do analysis of variance. So the reason we don't just do lots of t-tests is because of type 1 error. Type 1 error is rejecting the null hypothesis when the null hypothesis was actually true. In other words, saying, hey, we found something, when you didn't find diddly squat, all you found was random sampling error. Now, because we set alpha at 0.05 so often, then each t-test you do is like rolling a 20-sided die if alpha is 0.05. So here's a picture of a 20-sided die, and a man who very much loves that 20-sided die. So imagine that getting a 1 every time you roll a 20-sided die is like accidentally making a type 1 error. So if the null hypothesis is true, then 0.05, 5% of the time, 1 in 20 times, you will make a type 1 error. So if you're looking for a difference between 2 means, and your theory says there is a difference between the means of, high acid soil worms and low acid soil worms. Like if you were this godlike person who knew that there really was no difference, that acidity made no difference whatsoever to worm growth, but you're watching a researcher do over and over and over again these studies so carefully, high acid soil worms, raises them for months, low acid soil, compares their lengths. 19 times out of 20, if your alpha is set at 0.05, that researcher will make the correct decision if he or she is truly random sampling from all the possibilities. Even though the null hypothesis is false, 1 out of 20 times they will make the wrong decision. They will reject the null hypothesis and say, hey, we discovered that acidity affects worm length. 19 out of 20 times they'll make the correct decision and say, no, it didn't affect worm length. But one of those random times on average out of 20 times, 5% of the time, they will make the wrong decision. That's what alpha means, or at least that's one thing that alpha means. Alpha is your risk of creating a type 1 error, of committing a type 1 error if the null hypothesis is true. And of course, you don't know if it's true or not. So if the null hypothesis is true, your risk of committing a type 1 error on any one study is like rolling a 1 on one roll of a 20-sided die. You have a 1 in 20 chance of it happening. So what's the probability of at least one type 1 error happening on multiple rolls if the null hypothesis is true? Well, if you have 3 means, so maybe low acidity, medium acidity, and high acidity to grow your worms or something, then you will need 3 t-tests. You need to compare group A to group B, and the mean of group A to the mean of group C, and B to C. So you need 3 t-tests to cover all those possibilities. The true probability of at least one type 1 error happening in those 3 t-tests isn't 0.05 anymore, it's 0.14. That's a much bigger chance. So there's a pretty good chance that somewhere in there you're going to create a type 1 error. Any individual comparison, it's still 0.05. But if you step back and say, somewhere in there, is there a type 1 error? The answer is probably, yeah, it's getting more likely. And the more tests you do, the more likely that becomes. So if you roll the die 3 times, what's the probability that at least once it'll come up as a 1? It's 0.14. So if you have 4 groups and you decide to do all the t-tests, you have to do 6 t-tests. A versus B, A versus C, A versus D, B versus C, B versus D, C versus D. You have to do 6 t-tests to cover all the differences between all pairs of group means. So that's like rolling the die 6 times. And rolling the die 6 times, what's the probability that at least once it'll come up as a 1? What's the probability of at least one type 1 error somewhere? Now we're over 1 in 4. So we went from 0.05 for individual tests to 1 in 4 for all these tests. For all comparisons among 5 groups, you have to do 10 t-tests. Now the number grows kind of geometrically. The number of t-tests just gets bigger, and it gets crazy bigger, crazy fast. So for 10 t-tests, if you roll that die 10 times, what's the probability that at least once you'll make a type 1 error, that you'll come up a 1 on that 20-sided die? So if you do 10 t-tests, alpha is 0.05 every t-test, then the probability, if the null hypothesis is true, of making at least one type 1 error is getting close to half. 40% probability, 0.4. It's getting pretty unacceptable and crazy. So, and then 5 groups, it gets even crazier, and 6 groups, it's crazier, 7, it's even worse. It just gets worse and worse and worse. So to reduce our risk of type 1 errors, we often follow a strategy where before we do anything else, we do one decision, an omnibus decision. We ask ourselves, is there at least one pair of means here that differs? We don't do 10 different tests or 6 different tests or 3 different tests. We do one test with all the data in it at once. And this test is the analysis of variance. And the reason that works is because you can look at variability among means with a single procedure. So there's the mean for group 1, and it has its within group variance. The mean for group 2, it's within group variance. Group 3 within group variance. You pool that within group variance together and get the average pooled within group variance. And that's your estimate of how far apart individual observations should be from each other on average. And then you forget all the other observations and just look at the means. You calculate the mean of the means, which you have to do to get a variance or variability. And then you look at the variability of the individual group means around the grand mean. You pretend for a second that you only have one data set and its only points are your group means. So you have your between groups variance compared to your within group variance. And if the group between groups variance is bigger than you would expect, given what you know about how much individual observations are different from each other, then you say, hey, there's something going on. At least 2 means will be different. So let's run through this logic quickly. Which will probably be larger here? Between group variance or within group variance? So think about this. I'm not quite sure. I might say in this case, I could go either way. It's hard to tell graphically, but this is much more likely to go one way than the other. Now here, which one is most likely to be larger? I would say it's between group variance, because the within group variance is very small. When you average that together, you get a very small value. I know we're not using any actual numbers here, but that's fine. Whereas the mean of the means and the variability of your groups from the deviation from the mean of the means is much bigger. So here, you would say, yeah, there's a difference. At least 2 of these means are different from each other. And you did an analysis of variance. All we do is we add numbers to that and make it precise. That's the analysis of variance. You compare the variability among the means to your best estimate of the variability among individual observations, which is the average variability of all the different groups together. So here, I think it's quite likely you would not conclude that there was any significant difference between any 2 means, because there's a lot of overlap in those distributions, meaning there's a lot of within groups variability, but there's not much between groups variability. So the within groups variance is big for each of those distributions, each of those samples. When you average it together, it's still big. The average of big, big, and big is big. And you calculate the grand total, and the between groups variance is not terribly big. So you might say there's nothing going on here. So last slide in this little sub-lecture, how to do an ANOVA without any details. You calculate the between groups variance. We could call that sigma squared b. Textbooks have different ways to refer to that. You calculate the variance between the groups, in other words, the variance among the means. And you do that by treating each group mean as a single data point, and you look at the deviations from the total mean, and you look at the average squared deviation. So you just do a variance, but each group mean is one data point. What's the variance among the data points? Then you calculate the average within groups variance, sigma squared b. It's variance, so it's sigma squared. And so all you do for that is you calculate the variance of the regular observations in each group, which involves the deviations from each of their group means, which sometimes gets designated M sub G or X bar sub G, something like that. And then you average those group variances. So that's your within groups variance. You compare the between groups variance to the within groups variance by dividing. You divide the between groups by the within groups. So you're saying what percentage of the within groups variance is the between groups variance, right? And then you determine whether that ratio would be unexpected if the null hypothesis was true. Now I'm going to stop this lecture right here at this point. I'm going to head back to here, stop the screen sharing, come back to regular video. I'm going to stop the broadcast. I'll go into some details in a